myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about the register referenced instructions, memory referenced instructions, and IO instructions. At the end of this video, the student will gain knowledge about what is instruction format and what are its types, and how the register reference instructions can be grouped and can be applied, and what are memory referenced instructions and input output instructions. The basic agenda of this video is introduction, what is instruction set architecture, what are memory referenced instructions, register referenced instructions, and input output instructions. Basically, the computer can contains the two major parts. One is the hardware, second one is the software. The hardware is dealing with the physical components of the computer. The software is dealing with the programs. So here, the collection of programs that are written for one particular task is generally referred as software. The hardware is majorly focused on the microarchitecture, gates, registers, the devices, electronic devices, and the physics. So these are the major layers of abstraction in case of hardware. While considering the software, the major layers of abstractions are the application, algorithm, programming languages, machine code. So between this software and hardware, the instruction set architecture acts as an interface between these two components. While considering these layers of abstraction, the increasing order of abstraction can be from bottom to top order, and the increasing order of complexity is from top to bottom. So here these layers should not furnish the complete details. So these layers provide the abstract view of how the software components can be interacted with the hardware components through instruction set architecture. The user can have an interface and he can supply the program or command through application. And whenever the user want to construct a project, then or a program for one particular functionality, algorithm can be planned by the user. This algorithm can be converted into any programming language by writing appropriate syntaxes and rules, semantic rules pertaining to that language. After writing the code can be executed. First, it has to be compiled. The compiler can convert the high-level language program to the machine code, and in case of assembly language, by using the assembler, this assembly language program can be converted into machine code. This machine code can be taken as input for the instruction set architecture, and this instruction format, control memory instruction, micro instruction format can be applied to the micro architecture. This based on the micro operations specified in the micro instruction, the respective hardware devices can be activated and collaborated with the various electronic components, and the required functionality can be supplied to the user. So the instruction set architecture provides an interface between the software and hardware components of the computer. So through the application, in the example, the Netscape Navigator is used as example. So by using the operating system, the compiler and assembler can be used to convert the respective language program into the machine code. And the processor memory IO subsystem has to be used to activate the micro architecture of the computer with the help of micro instructions, and can be executed with digital design and circuit design. So between this software and hardware, the instruction set architecture can be placed. So an instruction set architecture is part of the abstract model of the computer that defines how the CPU is controlled by the software. It not only the instruction set architecture act as an interface between hardware and the software, but specifying both what the processor is capable of doing as well as how it gets done. Not only it is act as an interface, the instruction set architecture specifies the instruction formats as well as memory model, the data types, addressing modes, operating registers, types, and data addressing. So, with the programmer perception, the architecture is majorly concerned with the programs written by the humans, typically using the high-level languages to express the programming languages. Programmers learn to use language-based expressiveness and ease of use. With the programs, the functionality that has to be provided is to be expressed as a logic with the help of the programming languages in the user perception regarding the programming. So computer instruction set are limited by complexities. The instruction set is generally working with micro and nano scale of fabrication. So majorly concerned with the hardware components and physics and digital electronic circuits in order to act according to the micro instructions that are specified in the control memory of the computer. So thus instruction set is minimal refraction of high level operations and function set. It should be have number of limited hardware operations, transfer instructions, logic instructions, shift instructions, integer arithmetic, input output instructions, communication instructions. All these operations can be supported with the help of micro operations pertaining to that processor. The popular instruction set architectures are reduced instruction set computer RISC, complex instruction set computer CISC, minimal instruction set computer MISC, very long instruction word VLIW, explicitly parallel instruction computing EPIC, one instruction set computer VERSIC, zero instruction computer JEDI SC. Okay, so these are the popular instruction set architectures available in the market. So instructions may be having several kind of categories. Each instruction set architecture generally consists of the arithmetic instructions, logical instructions, shift instructions, input output, computer operational units to activate various communicational instructions can be available. Apart from that, the instructions may be broadly classified into two categories: conceptual application or meaning, performance based on location of operation. So majorly, there are two varieties of applications. They are the CPU bound applications and IO bound applications. If the program involves majorly, major part of the program involves the arithmetic operations which requires the CPU processing, those those applications are generally considered as CPU bound applications. When the applications required major part of the application depending upon the input output operation, those applications are categorized into IO bound applications. The IO bound applications comes under the category of performance based on location of operation. So based on this location of operation, the performance of the programming can be affected. So in this based on performance based on location of operation, three categories of instructions are generally available. They are register referenced instructions, memory referenced instructions, and input-output reference instructions. So the instruction format can be, each and every instruction can be divided majorly into two parts, the opcode as well as the address. So here the instruction register is capable of holding 16 bits 0 to 15. 0 to 11 bits are generally used to specify the address. So the location of the operand can be specified by using the address field. Next, 12 to 14 bits can be used to specify the opcode. The opcode specifies the micro operation that can be applied on the data available at the specified address. The 15th bit is used to specify the mode of the addressing. There are two possible modes, direct mode and indirect mode. The direct mode and indirect mode can be identified with the help of I value. When I value is 0, it is considered as a direct mode. When I value is equal to 1, then it can be considered as indirect mode. In the direct mode, the operand can be available at the address that is specified in the instruction format. In case of indirect address, the effective address of the operand can be available at the address part of the instruction. So here the three categories of instructions are memory referenced instruction, register referenced instruction, and input-output instruction. Memory referenced instruction, the opcode can be ranged between 000 to 110. In case of register referenced instructions, the opcode is 111, but the I value can be 0. In case of input-output instruction, the opcode is 111 and the I value can be 1. What are register referenced instructions? So in the register referenced instructions, the opcode can be 111 and I value can be 0. Those instructions generally referred as register reference instructions. So these instructions referencing CPU registers for data processing. The CPU registers, we are having categories of registers here. The general purpose registers that are available in the CPU are used for data processing. They are ranging from R0 to Rn-1 depending upon the processor. And few data access possibilities can be available in the register reference instructions. Two registers are majorly involved in these type of instructions. One is the accumulator, AC. It is used for arithmetic, logic and shift operations and also used for input-output operations. The second register is E-bit, E-utility flip-flop. Used in shift operations, may be used in arithmetic operations to store the extra bit or overflow bit generated as a result of arithmetic operations. These two are involved in the generally the register reference instructions micro operations. What are various list of register reference instructions? So here the first instruction is CLA. CLA means clear AC, accumulator register can be stored with 0 value. Next CLE, clear E. E flip-flop can be cleared. CMA, complement AC, accumulator can be complemented. Next CME, complement E, E value can be complemented. CIR, circulate right shift AC and E along with E register, AC value can be circularly right shifted. CIL, circulate left AC and E. So circular left shift operation can be applied on AC in conjunction with the E. INC, increment accumulator. SPA, skip next instruction if AC positive. If AC contains the positive value, skip to the next instruction. SNA, skip next instruction if AC is negative value. Next, SJDA, skip next instruction if AC is 0. SJDE, skip next instruction if E is 0. HLT, halt computer. So these are the list of instructions that are available under register referenced category. So grouping of these register referenced instruction depending upon the registers they are used. So we already know that two registers are generally involved here. One is the accumulator and the E flip-flop. So based on the accumulator affected instructions are CLA, CMA, CIR, CIL, increment, SPA, SNA, SJDA. These instructions can affect the accumulator register value. And the category of CLE, CME, SJDE can affect the E bit value. HLT is used to control affected halting the computer. So what are the clear, complement and increment of the AC resistor? In the RTL, how they can be represented? So CLA can be used clear the accumulator. So 0 value can be loaded into the accumulator. Next, CMA is complement the accumulator. So accumulator value can be loaded the complement value, the ones complement by interchanging 0 as 1 and 1 as 0. Next, INC means incrementing the accumulator. The value stored in the accumulator can be raised by 1 value. Next, clear complement E register. Those can be represented in RTL as CLE. So, E register can be loaded with 0. So, CLE clear E value. So, 0 value can be stored in the E flip-flop. CME means complement. So, one's complement of E can be stored in the E flip-flop. Next, the shift operations, how they can affect the resistors. So, this is a circular shift that is performed using the E register. Control over timing ensures all operations operated in parallel. Along with AC resistor, along with E, circular shift operation can be performed. The two instructions that come under this category are CIR. So, here in the CIR, circular right shift operation can be implemented on AC along with E. So, in the AC 0 to 14 bits can be loaded with AC 1 to 15 bit. AC 15th bit is loaded with E and AC 0 bit can be stored in the E flip-flop. So, these are the RTL operations that can be performed during the circular right shift of AC along with E flip-flop. What is CIL means? Circular left shift. So, this circular left shift operation can also be accomplished on AC along with the E flip-flop. So, here AC 0 to 14 bits value can be stored in AC 1 to 15 and E flip-flop value can be stored in the AC 0 and AC 15th bit value can be loaded to the E flip-flop. So, these operations accomplish the circular left shift of AC along with the E. So, here circular left shift and right shift can be performed on AC along with the E. Next operations are the skip operations in the register referenced instructions. So, skip on condition on the AC register value. Test the sign or value status of 2's complemented integer in the AC. If status matches, if the condition specified matches, advances PC by 1 instruction word. So, the instructions that comes under this skip instruction category are SPA, SNA, SJDA. So here, if AC value is greater than 0, then PC can be incremented by 1 value. That means if AC contains the positive value, then PC can be incremented by 1. The next instruction, it has to be skipped. Next, SNA means AC is less than 0. That means AC contains a negative value. PC value can be incremented by 1 to facilitate to skip to the next instruction. Next is SJDA. When AC is equal to 0, PC is incremented by 1 to skip to the next instruction. On the E register, the skip instructions are: test the status of E bit. If not 0, proceed to the next instruction. If 0, advances PC by 1 instruction. So the instruction that comes under this category is SJDE. So here negation of E can be taken, and in case of that, the PC can has to be incremented by 1. So the last instruction under the category of register referenced instruction is halting the computer, disable all the circuits. So these are variety of register referenced instructions. They can be grouped as the clear complement instructions, the shift instructions, and skip instructions. The next category of instructions are memory referenced instructions. Once an instruction has been loaded into the instruction register, it may require further access to memory to perform its intended functionality. This instruction can be the direct access or the indirect access. Access the storage at the specified instruction register address can be done in case of direct access. In case of indirect access, first transfer to the direct DR to the data store at the specified IR address. Access this fetched address to perform the required function. So here, in case of indirect address, 2 location moves can be required in order to identify the actual operand. The effective address of the operand can be specified in the instruction format in case of indirect access. And the list of instructions that comes under the category of memory referenced instructions are AND memory word to the AC. So here the AND logical operation can be performed. And the second instruction is add memory word to the AC. Arithmetic addition can be performed. LDA means load memory word to AC. STA, store content of AC in the memory. BUN, branch unconditionally. BSA, branch and save return address. ISJet, increment, skip if 0. So these are the list of instructions available under the category of memory referenced instructions. So what are the direct access instructions comes under the category of memory referenced instructions? How they can be notated by using the RTL. The first instruction is AND instruction. So here the data register can be loaded with the address register pointed memory value, and the AC can be and logical AND operation can be performed between the data register and the accumulator register. So this is the RTL notation of the AND operation. How the addition can be performed. So the data register is loaded with the memory word that is pointed by the AR, and the between AC and DR the add operation can be accomplished, and the result is stored in the AC. Next instruction is LDA. So here memory location, what is the value stored at the memory location pointed by AR to the DR, and the DR value can be loaded into the accumulator. In case of STA, accumulator value can be loaded to the DR and DR can be loaded to the memory. Memory transfer has to be taken place at the location specified by the AR. Next, BUN means branch unconditionally. The instruction register 0 to 11 value can be considered here in the AR register, and AR value can be loaded to the PC value. Next, ISZ means here BSA is IR 0 to 11 value can be stored in the address register and PC value can be transferred to the memory location pointed by AR, and AR can be incremented by 1, and this value can be stored in the PC. ISZ means IR 0 to 11 value can be stored in the AR. Memory location of address register can be initialized to the data register, and DR value can be stored to the AC. AC can be incremented by 1, and AC value can be stored in the DR. Next, DR can be loaded to the memory address, and PC can be incremented by 1 when AC contains the value 0. When this condition is satisfied, then only the PC value can be incremented by 1. In the indirect address instructions, how the AND and add operations can be performed. Here in the indirect address, the effective address of the operand can be specified in the instruction format. Hence, 2 locations can be moved, 2 cycles are required in order to access the operand. So here instruction register 0 to 11 bit can be stored in the AR, and the memory address register pointed memory location value can be stored in the DR, and DR register 0 to 11 bits can be transferred to AR, and the memory location pointed by AR, the value can be stored in the DR, and between this data register value and the accumulator value, the AND operation can be performed. So here this is the location. One cycle can be required for accessing the effective address. At that location, to move the second cycle can be required in case of direct access instruction, indirect address instructions. Next, similar way the data can be loaded in the AC as well as in the DR register. DR register can be used 2 cycles to locate to the required operand. After acquiring the required operand in the DR, along with AC, the arithmetic addition operation can be performed in case of add instruction. In this way, in the indirect address, the DR register can acquire the operand by using the 2 memory cycles. How the transfer of instructions can be taken place in case of memory referenced instructions. So copy data or from memory and CPU can be accomplished through transfer instructions. So loading refers to memory to CPU transfer. Storing refers to CPU to memory transfer. 2 types of transfers can be accomplished. So that is memory to CPU or CPU to memory. Loading means memory to CPU transfer. Storing means CPU to memory transfer. So LDA instruction and STA instruction comes under the category of transfer instructions. LDA is loading instruction. So memory to CPU transfer can be accomplished. So here the address register pointed memory location value can be loaded to the DR register, and the DR register value can be loaded into the accumulator. In case of STA store instructions, The storing refers to CPU to memory. So, accumulator value can be first transferred to the DR register. DR register value can be transferred to the memory that is pointed by AR register. So, these two instructions, LDA and STA, comes under the category of transfer instructions. How the addition and AND instructions can be done. So here logical AND is done on all bits in parallel. So how the register capacity can be considered here. On respective bits parallelly the addition and operation, logical AND operation can be applied. Numeric 2's complement addition may be done in serial or in parallel using look ahead circuit. So this is the data register and this is the AR register. AR register is used to point a location in the memory so that from the memory the operand can be accessed and can be stored in the DR register. The DR register value and with the AC value the AND or add logic can be applied. So DR register holds the one operand, AC can hold the second operand. Between these two operands, either the arithmetic add operation or logical AND operation can be performed in the memory referenced instructions. So AND means here the memory location that is pointed by AR where the operand is located. From that location it is transferred to the DR register. And after that, between AC and DR register, the logical AND operation can be performed. In case of add, the first operand can be available in the DR with the help of memory location access by the AR register, and AC and between DR register the addition operation can be accomplished. The next category of instructions in the memory referenced instructions are the branching. Instructions that explicitly modify the PC during execution are generally referred as branching. They can generally alter the program control sequence. Program execution sequence can be altered with the help of these branching instructions. This implies that next instruction to be executed is not located in the next continuous word of the storage. Use it to program if then else decision control and while do repetition control constructs in the high level language. So by using these control structures, how in the high level language the program flow can be altered. In the similar way, by using the branch instructions, the micro instruction execution sequence can be altered by modifying the PC value during the execution of the micro program. The first instruction under this is BUN, branch unconditionally. There is no checking of condition can be done in case of branch unconditional. So it can branch when the instruction, when the program identifies the BUN instruction. The IR register 0 to 11 bits can be loaded to the AR register. And what is the AR register contains that is transferred to the PC so that the sequence of program execution can be altered without checking the condition by using the BUN instruction. The next category of branch instruction is branch and save instruction. So used for programming subroutine calls. Subroutines are small programs. They can be called as and when required. These subroutines facilitates the reusability. Whenever a subroutine call encountered, the program stops its execution and the control transferred to the subroutine. And the instructions that are specified in the subroutine can be executed one after another in a sequence until the return statement. Whenever the return statement is identified, the control is transferred to the main program. So here the BSA instruction come under the category. So here the instruction register 0 to 11 bits value, the address is moved to the address register, and PC is moving to the memory location that is pointed by address register. PC value can be modified with an increment value of AR register plus 1 so that the required subroutine can be serviced first. Increment and skip if 0 instruction. So here used to implement a counter based do while construct as in case of high level language. Similar way you can use the increment and skip if 0 instruction. So that can be mentioned as ISZ. And what are the operations, micro operations that can be performed in case of ISZ can be denoted in the RTL. First, the address register has to taken the 0 to 11 bit of the instruction. And the data register contains the data value that is pointed by AR from the memory. Data register value can be moved to the AC. AC can be incremented by 1. So AC value can be moved to the DR. DR has to be moved to the AR specified location of the memory. And when AC contains 0, then PC value can be incremented by 1. So the skip operation can be performed if it all 0 value they present in the accumulator. If this condition is satisfied, then only the next instruction has to be skipped. So here the condition checking can be done. The next category of instructions are input-output instructions. They are generally used to facilitate take data by using the various peripheral devices. So used for communicating data between CPU and I/O peripheral devices. Various peripheral devices are connected to the computer like keyboard, and by using the keyboard, the data can be taken, and with the help of the video, the output can be represented to the user. So what are the various devices? I/O devices are connected to exchange data transfer between the CPU and I/O devices. These category of instructions can be used. The list of instructions that are available under this category are INP, input character to AC, OUT, output character from AC, SKI, skip on input flag, SKO, skip on output flag, ION, interrupt on, IOF, interrupt off. So the input devices, whenever required the CPU service, they can acquire the service by raising the interrupt. To facilitate these interrupts, ION and IOF instructions can be used under the category of input-output instructions. So what are the simple IO instructions and how they can be perform various micro operations? The first instruction is INP, input ASCII character, OUT, output ASCII character, SKI, skip if input flag is 1, SKO, skip if output flag is 1. So here FGI, FJO are the input-output flags. If they contains the value 1, then the skip operation can be performed. So each peripheral device has a communication and control interface that interacts with the computer interface logic circuit. This is generally referred as input-output processor. The input is need a data transfer, INPR, and a flag FGI indicating buffer empty or full. With the help of INPR register and the FGI flag, the input operation can be performed. Similar way, the output operation can be performed by using the OUTR register and FGO flag. So how these input-output operations can be carried out? So here the keyboard is taken as a sample input device. So here the interface can be used. Generally the input-output processor can take care of it. So here this is the interface between the CPU and the input device, transmitter interface, and this is the INPR register. The data can be first transmitted to the INPR register. From these, it can be transferred to the accumulator low order bits. And here, by checking the FGI flag, the transmitted interface can be activated. These operations can be performed during the input. How the output operations can be performed is by taking the character from the accumulator lower order bits to the output register OUT, and from this the receiver interface can receive the characters and it can check the flag value of FGO and can send to the output peripheral device. The example considered here is the printer. In this way, input and output operations can be performed with the help of INPR and FGI for the input and OUT and FGO for the output. And whenever the input-output devices require the CPU service, they can gain the attention of CPU by raising the interrupt. Input-output interactions with electromechanical peripheral devices required huge processing times compared with CPU processing times. Why? Because the peripheral devices are generally electromechanical devices and the CPU is an electronic device. There is a synchronization mechanism can be needed between the input-output and the CPU. I/O can be performed in the milliseconds, but CPU can process in the nano or microseconds. So interrupts permit other CPU instructions to execute while waiting for I/O to complete. So need an additional 1-bit IEN flip-flop to store the interrupt status. Whether interrupt is occurred or not can be identified with the help of IEN flip-flop, interrupt enable flip-flop. So the two instructions comes under the category of I/O instructions are regarding interrupt is ION interrupt enabled. That is, interrupt is on, IEN can contain the value 1. IOF means interrupt disabled. IEN can store a value 0. With the help of these two states, the system can recognize whether the interrupt can be enabled or disabled. So in this approach, interrupts are used only with I/O handling. In addition to a flip-flop stored the interrupt enabled state, one more flip-flop can also be used, that is the R flip-flop, to indicate ready or not ready state. In general, interrupts may be used with arbitrary instructions for exception trapping and handling. So here, based on the one more flip-flop can also be used for the recognition of interrupt, that is the R flip-flop. Now we have to discuss about how this interrupt cycle can be occurred. With the help of R flip-flop, whether the system is executing the interrupt or an instruction can be easily identified. Generally, the instruction can contain the 4 steps. Fetch the instruction, decode the instruction, fetch the required operand or calculate the effective address. Next, execute the instruction. After this first step, the instruction cycle can check for the interrupt by looking into the R flip-flop. If R is equal to 1, then interrupt cycle execution can be started. Immediately it has to stop the execution of the current instruction and shifting the PC value to the stop, and it has to move to the interrupt service routine. Start executing the interrupt service routine. So here store return address in the location 0. So the PC value can be stored in the memory location 0 and the branch to the location 1. PC has to be given a 1 value. Reset interrupt ready. IEN can be 0 or can be 0 in order to serve the interrupt service routine ISR. In case of R is 0, instruction can be executed. So fetch decode instruction cycle can be taken, and here if at all the instruction contains the input output operations, then it can check for IEN whether it is enabled or disabled. So if at all IEN is enabled, then it can check for whether it is an input device or output device by looking into FGI and FGO. If at all FGI is 1, it is pertaining to the input device, so it has to take and 1 value can be stored to the R by indicating that an input interrupt can be occurred. If FGO is on means taking by making the value 1 to the R flip-flop in order to indicate that output interrupt is occurred. So in this way, the interrupt cycle can be executed to facilitate the input-output operation. And the two instructions that can be used to check the these interrupt enable or disable are ION and IOF. So in this video, we will discuss about what are register referenced instructions and what are memory referenced instructions, what are input output instructions, and what are the various micro operations that can be performed under each category with RTL notations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.